Hi, I'm Amogh. I work as an engineering manager at Helpshift. My relationship with Clojure started 7 years ago and still continues to be. This talk is a product of my curiosity. I have this habit of looking at things and often wondering why things are the way they are. And this habit sometimes takes me into rabbit holes of things, and that's what this talk is about. Uh, all this time that I have worked with Clojure, there are interesting design decisions that the language has, and I often wonder why a certain syntax is like this, why certain choices were made, and while trying to figure certain things about polymorphism offering in Clojure, I went through a similar journey and I went all the way back to the very genesis of polymorphism. So that's what we'll do in this talk. We will start way back. We'll go back in history and look at when did polymorphism start, and we will slowly see it transform itself into in the current form that Clojure offers in its API. Of course, we have to do a bit of etymology. Polymorphism comes from two Greek words. Poly means many and morph means form. So the basic idea is that anything that exists in more than one forms, right? Now, in the context of Marvel Cinematic Universe, I have coined the term polymorphism in MCU. It's here. But let's look at more credible sources of polymorphism in greater fields of study. Now, here is polymorphism in nature. So here's polymorphism in nature. You can see there are two types of jaguars. They're essentially jaguars, but they are slightly different. The coat color is different. The way their spot patterns are, that's different. So in biology, there is this term called phenotype, which is essentially a set of attributes that you observe for an organism or a certain species. And when there are variations in those set of attributes, is when you observe polymorphism in nature among that species. So as we can notice that even in nature, you don't have really finite types of organisms. Any permutation and combination of species, right, in various attributes leads to a different type of entity. Here we have somehow managed to name two of them, but that's not enough. So now let's come back to computer science, which is one step closer to getting to Clojure. Polymorphism first entered computer science in early 1960s when this gentleman on the left, he was a professor at Cambridge, Christopher Strachey. Christopher Strachey and the team at Cambridge were working on this programming language called CPL that was mostly academic in nature because it never saw the light of the day and it was never really used in production. A lot of work was for academic purposes, but a lot of early ideas of polymorphism were presented in a paper which were based on lecture notes that Professor Strachey took in various universities. So a CPL, as you can see, it's a very old language and it influenced many other languages, and C also has roots in CPL. Some of those ideas transformed into C. So one of the ideas about polymorphism that the CPL team talked about was basic polymorphic operators like simple addition or multiplication. In this case, we are looking at addition, right? You can add two integers. You can add two floating point numbers, which is a completely different, floating point arithmetic is a completely different thing. And when you're adding a floating point number to an integer, it's a very different algorithm. You have to add upcasting and convert the integer to a float. So these are three different types of operations that are essentially happening, but they're all being represented by one symbol, which is the plus operator. So this is what the early idea of polymorphism was. And in that paper, Christopher Strachey categorizes polymorphism into two broad categories. One is parametric, and the other is ad hoc. So in parametric polymorphism, it is type agnostic. You can see this in action in Haskell. If you have worked with generics in Java, you can see that in action there also. The general idea is that your algorithm, your code will be type agnostic, and wherever types are needed, they will be replaced by placeholder variables. And when invoking that piece of code, say instantiating a class in case of Java, or say calling a function, these actual types will be passed as parameters, and they will replace those placeholders. But the algorithm works irrespective of the type. So this is a more systematic way of polymorphism called parametric polymorphism. The other polymorphism was ad hoc polymorphism, where for every type, there is a different definition of the function. And the example that we saw of the operator, any arithmetic operator as such, right, is an example of ad hoc polymorphism. And they go well together because, say, you can have a generic algorithm that works irrespective of the type, but at some point of time, you have to do type-specific operations, and that's when ad hoc polymorphism comes into play. Now, these are all compile time examples of polymorphism in languages where type system was compile time. Now, here we are far away from Clojure, because for that, runtime polymorphism has to exist. So now we are in mid-60s, somewhere in 1965-66 in Norway. These two gentlemen on the left, Ole Johan Dahl and Christian Nygaard, they were working on a programming language that was meant for simulation software that would simulate industrial processes. And in the process of working on this language and its final draft, they came up with a concept of what we today call as traditional object-oriented programming and class-based inheritance. So all of these ideas that we see in languages like Java, C++, Python, Ruby, they all have roots in Simula. So what's the general idea of runtime polymorphism that was accidentally brought because of object-oriented programming? It's worth mentioning that the term object-oriented programming was coined a little later when Smalltalk was made, but the current form of object-oriented languages follow the Simula model and still use the term object-oriented programming. So, I mean, so we all have seen a diagram like this when we learn object-oriented programming and inheritance in general. So as you can see, say for example, you have an application which is a messaging application. It has three types of messages. You can send a text message, you can send an image, and you can send a video message. They all render differently, and this is where polymorphism come into play, because you have to render all of these different types of messages, and when you're rendering, the rendering logic for all of them is hidden from the person who is calling the render or on render function on the message object, right? So here you can see, so how this typically works is, if you're calling render on the message object, you do a traversal through this hierarchy. You have to check the class of the object message and then look for the definition of render in that class. If it's not present in that class, then it goes to the parent class of that class and tries to find the definition. But for the caller who is using this function on the object, they don't have to worry about the exact implementation of how a particular message is rendered. So the benefit of polymorphism is there, but is achieved at runtime, and there is some performance cost associated with it, and we will get to that later. So as I said, Simula had a lot of influence. Over the years, languages that adopted object-oriented programming adopted a lot of ideas that were there in Simula, and that's what we have, and that has kind of fortunately or unfortunately, become the mainstream programming model. But it also influenced the Common Lisp community. I think somewhere in 1970s or 1980s, there was this phase where the Common Lisp community also were trying to somehow get object-oriented programming ideas, because some of those ideas were really good, like runtime polymorphism, into Common Lisp. At MIT, there was an extension to Lisp called MIT Flavors, and there was another extension, I think, at Xerox PARC. They're working on something called as loops. And the ideas in both the extensions came together under a new effort called Common Lisp Object System. Now you can see I have a basic syntax out there. There is some Common Lisp code. It's understandable. There are 3 types of messages inheriting from the message class. But what is different here, if you notice, right? The method doesn't belong to the class. It is outside of the class. So what happens is that Common Lisp still had all these higher order functions, and you still had to work with these methods just as you work with normal functions. So this is what it allowed. You could have a generic function like this with various different implementations based on its argument, and at runtime it would figure out which version to call. Now we are much closer to what kind of polymorphism in Clojure looks like. So we are here at Common Lisp object system. Now let's look at now this dispatch mechanism that we saw earlier, right, with somewhere here, is called single dispatch, because you are looking at the object and you're looking at the class of the object and deciding which version of the render method you have to invoke. But sometimes what if you have a use case where you have to take a message and then you have to send it to a different channel. It could be you have to send a message via SMS, via email, via WhatsApp. The rendering logic is different. The API for sending data to that particular channel is also different. So your logic will have permutation combination of these 3 types under each hierarchy, right? You will have 9 different possibilities. But how do you achieve this? Because your dispatch is only going to happen on the object, which is message. And if you're going to pass a channel to it, the dispatch on channel is not going to happen. So in the single dispatch world, or the Java world, I would like to call it, this is what you end up doing. You use a design pattern to achieve the same, because you want to dispatch on the 2 arguments. So you essentially define an interface, and for one interface represents the first argument, which is the message. You typically pick one out of the 2, the one that won't change often. So for example, if you expect your business to have more messages in future applications, right, in future versions of the apps, next releases, then you make that your visitor, and then you have implementations of a visit function per visitable. Each visitable is the other child of the other hierarchy, right? In this case, these are channels. And what they do here is that the channel interface itself here will have a accept method which accepts a visitor. And there is a neat trick here where each implementation of the accepts the visitor, which is a concrete visitor, when passed, and that's when the first dispatch happens. Then it calls visit on the visitor and passes itself as an object. And that's when the second dispatch happens. So essentially what happens is that you will end up implementing, every time you have to add a new type of message, you will implement a message visitor here, and implement all the visit classes for visit functions for different channels. So it is easier to add a new message but you will have to end up updating all the existing visitors if you have to add a new channel. So you have to make a choice here. And this is how you will end up typically using it. So what you realize that I spent 4 slides trying to come up with a usage, which is just the last 3 lines. Now let's look at how something similar is achieved in a language, or say an extension to the language that was done 20 years, roughly 20 years before Java came onto the scene. This is the same code written in Common Lisp. You have your hierarchies in the first image. In the second one, you have you can see it's the same generic method, but then you have implementations for combinations of all messages and channels, and you have total of 3 into 3, 9. But it's much easier to add a new combination, and if you want to continue with a older variation of or you want to continue with a generic variation, you leave a parent class implementation and do not have an implementation for the child class here. And that's the usage. So the code is much shorter, and this was possible in Common Lisp object system somewhere back in 1970s. Now let's look at the Clojure version of the same solution. Now Clojure's take was a little different because of the preference for having open maps and data. Clojure provides you a derived form where you can have hierarchy without classes. So what you end up doing is you can define your hierarchy using keywords or symbols. And you can also, what you can also do is, you can, because you play well with Java, you can also take Java classes and bring them to the same hierarchy. And this Clojure maintains this as a global registry. You can create your own hierarchy so that it doesn't mess up with the global one. That's possible. But what you can see here is that you're not dependent on the idea of class here. You have open maps. Dispatch happens with a function that accepts the argument and then decides which method to invoke. The function returns a dispatch value. That dispatch value is matched against all registered method implementations. And at runtime, it decides, okay, this implementation is supposed to be called. This is an expensive operation, and that's why the multi-method source code I have seen, what it does is that it caches dispatch value to dispatch method mapping and adds some sort of performance to this approach. So while multi-methods are expressive, but they lack a little bit of performance when you really need it. So much later, Clojure came up with a more performant solution to runtime polymorphism, which was protocols. Protocols are very similar to Java interfaces. In fact, what you get out of this code is an interface by the same name in the same namespace. I mean, in Java world, it's called a package, and all these implementations belong to the same namespace. And as you can see, you don't have to create an object. You can still call a function or a method as if it was a regular function. So your functional programming semantics remain the same. It plays well with Java interop, leverages JVM level optimizations. It is faster than multi-methods, but it sacrifices some of the expressiveness. So what I would say is that if you're writing an application which is complex and your rules in the business logic can change more often, you would be happier starting out with multi-methods. But if you anticipate much earlier that you would need performance out of a system, for example, if you are building a library that deals with databases, and consumers of your libraries won't have control over the library. So, and they might end up using it in hot code paths, right? Where this little performance gain will be advantageous to them, then you would rather stick with an implementation in protocols and records. You will lose out on the inheritance hierarchy that you get. But what you gain is performance. So essentially the call is between when do you need expressiveness and when do you need performance. A good example of a library that uses multi-methods well is Integrand, and it also leverages database hierarchy, and it doesn't hamper the performance much because it manages state of your application. So most of the multi-method lookup happens when you start a component or when you stop a component. So if your library is of that in nature, or if your code is of that in nature where you know that the performance doesn't matter to you right now, you can always start out with a multi-method system which is far more expressive. On a closing note, I will leave you with a quote from a paper that Christopher Strachey wrote from his experiences with CPL. And while he was trying to go through different forms of polymorphism, he considered for a while that runtime polymorphism might be a good idea, but determining type at runtime is an expensive operation for machines of those times. But he does say that if there is an old idea which seems logically satisfactory, but perhaps the current environment or the current systems in those cases, those current machines of those times were not conducive for those ideas, we should not reject an idea like this. And we have seen that this was written somewhere in 1960s, and runtime polymorphism really became popular much later, and machines also became a lot more powerful, so that this runtime check wasn't that big a problem for a lot of applications. So on closing note, what I would like to say is that it is important to sometimes look at history, because there are these ideas that sometimes get lost or get rejected because the environment then is not ready for those ideas, but maybe the environment now is ready for some of those ideas that were written then. So things that people document in papers, in research papers, some of those ideas are worth revisiting, because maybe in today's times they will matter even more. That's all I have. Thank you. Any questions anyone has?
So I actually like that conclusion a lot, because it's something that I've been thinking about a lot lately. The space that I've been thinking about it in is largely data and disk related, but I'm curious, beyond the papers and the research that you addressed, are there other things that you've seen recently where you're like, oh, this idea is from like the 70s or 80s, but it's actually really cool and applicable now?
Not that comes to my mind right away, because most of what I had researched is here in these slides. Maybe I will write a blog post about it in detail, because some of those ideas I couldn't put in condensed 20-minute slot. So maybe I will write about it. Anyone?
I think we'll have to do them over chai.
Okay, I think we have a coffee chai break coming soon. If you guys have any questions, if you want to talk about some concept, because I know some of that code around the implementation of design pattern was a little terse to understand the speed at which I was moving the slides. So if there are any questions around that, and I would like to have a discussion. If you have a different opinion, I would like to hear that too. Thank you.